Good evening, everyone. Thank you for joining us tonight for the first event of this year's RiverWatch Fall Speaker Series. For those of you who are not familiar with the Illinois RiverWatch Network, RiverWatch is a citizen science or community science organization that trains volunteers to monitor water quality in their own communities. The mission of RiverWatch is to safeguard the future of Illinois rivers and streams through stewardship, education, and sound science. Before we get started, I would ask that you keep your microphone muted during the presentation to limit the distracting noises that might show up. We will have a Q&A session after the presentation, so if you have a question along the way, you can either put it in the chat box to be answered at the end, or you can save the question to ask aloud. Tonight we have with us Dr. William Hintz, or I'm sorry, I don't know if it's Hintz or Hintz, of the University of Toledo, and his doctoral candidate, Bayley Wilmoth. They'll be talking this evening about some of their work studying how adding salt to our environment is impacting freshwater ecosystems and sharing information about alternatives to the use of road salt. And with that, I would like to welcome our speakers for the evening.
Thank you, Janelle. I appreciate the invitation. It's great to be with you all tonight. I'm just gonna share my screen here quick. Can you see this okay?
Yep.
Great. So as Janelle said, I'm Bill Hintz. I'm an assistant professor at the University of Toledo, and with Bayley Wilmoth, we'll be talking a little bit about the ecological consequences of rising salinity in our freshwater ecosystems. For the most part, my lab studies how multiple stressors in freshwater ecosystems affect organisms in the environment and their interactions. And so, Bayley, do you want to introduce yourself briefly?
Sure. Thank you very much for having me. My name is Bayley Wilmoth. I am a PhD student in Dr. Hintz's lab, and I am currently studying how salt interacts with other potential environmental stressors. They could be environmental pollutants from humans, or they could be naturally occurring stressors such as predation or competition. And how those interact to alter our freshwater ecosystems.
Yeah, so today we're going to kind of give you a flavor of the ecological impacts. And so we're going to we have a lot of information to present to you tonight. And, we look forward to answering some of your questions, at the end of the talk. So as many of you know, if you're familiar with Danelle's work, she's published a few papers in the last few years on the impacts of road salts. And so we have this giant salt problem, right? And that salt problem is created from a whole host of factors, one of them being global climate change, which is changing precipitation events around the world, which changes kind of the water budget of streams, lakes, and wetlands, and is causing sea level rise, which is a threat to coastal freshwater ecosystems. And there's agricultural induced salinization, which on a pretty massive scale, we're applying salts to farm fields, things like potassium chloride, and those salts can wash off of farm fields into adjacent freshwater ecosystems and move their way downstream. And then there is mining induced freshwater salinization and this extraction from a bunch of material from the earth. During precipitation events, a lot of the salts in the tailings of mining operations can dissolve and wash into adjacent streams, rivers, and wetlands, and eventually make their way to lakes. So, and then one thing we'll be talking about tonight, one cause of freshwater salinization is the application of road de-icing salts. And that's something my group has been studying for about 7 years, me and my collaborators. And so we'll talk about that a little bit more here. When we think about road de-icing salts and this kind of larger issue of salt pollution, it's a difficult issue to address, right? When we think about the benefits we derive, the benefits your friends, your family derive from the use of de-icing salts, they reduce accident rates by some estimates 87% on 2- and 4-lane highways during winter travel conditions. And so we derive a pretty significant benefit from the application of de-icing salts, and that's mostly manifests in our safety during, adverse winter conditions, but also the transport of economic goods during the wintertime, keeping roads open, right? And keeping the economic engine of the United States moving forward. So there's a very, intense need for de-icing salts. And when we think about that need around the United States, about 70% of road networks and 70% of the United States population lives in regions that experience snow and ice during the winter months. And in those regions, there's a massive amount of road de-icing salt applied for the reasons I just mentioned. When we think about how many, let's just put it in pounds, can be applied annually to our roads, it can get upwards of about 66 billion pounds. That's a lot of salt used for de-icing purposes during any given year. And obviously that salt has to go somewhere, and it eventually typically makes its way into our freshwater ecosystems. When we try to contextualize this application of de-icing salts, if you think about a small kitchen table that maybe 4 people can fit around, and you imagine taking your typical table salt and pouring about 18 pounds in the middle of that small kitchen table, that's about how much we can apply in some regions to our roads. And so that's a lot of salt. And freshwater organisms, are used to fresh water, right? By definition, fresh water is really low in salinity. And so most freshwater organisms has a very distant evolutionary history with high salinity. So this rising salinity in fresh waters is of concern. You've probably seen something like this if you're from the St. Louis area. When you get a good winter storm, this is actually where I study the ecological impacts of road de-icing salts. This is our parking lot and the sidewalk into the building I'm in currently. And this is just a photo that I've seen, I took a couple years ago. And so, think about on a massive scale, all the parking lots, sidewalks, and road networks that can be covered in de-icing salts. That has to go somewhere. And in the picture on the right, Lake Erie is just beyond that tree line. So really close to where we pull our drinking water from, actually, in the region we're at. So one driving question behind our research is, what are the ecological impacts once road salts get into freshwater ecosystems? And we'll talk about that a little bit here now. So one common theme in the scientific literature is that we get this reduction in the diversity and abundance of zooplankton. Why does zooplankton matter? Well, they consume all the algae, or a lot of the algae, in freshwater ecosystems, and then those zooplankton are consumed by pretty much every fish species once it's first born, right? So these zooplankton play a critical role in freshwater ecosystems. And what you're seeing on the left here is that greenish hue. When we lose that grazing pressure from zooplankton because the salinity has become too high, that's an excess of algae, phytoplankton, right? And that greenish hue comes from the photosynthetic algae in the water column. So this is kind of a photo from some of our experiments on road salt. So when we think about the context for the loss of these zooplankton, if we start at the red X here and we lose a lot of these zooplankton, what we're trying to figure out scientifically is, what are the bottom up and cascading effects of this? So if we start at the X and we get more algae, like I just showed you on a previous slide, that could shade out a water column, right? And reduce sunlight penetration into the water column and possibly affect macrophytes in lake ecosystems and benthic organisms. But really, when we think about the fish that eat the zooplankton and then the larger fish that eat the smaller fish that eat the zooplankton, right? There's as I say in my ecology class, everything is interconnected. And so when we lose these zooplankton, we need to think about the larger food web impacts in freshwater environments. We've observed some direct effects of road salt contamination on a lot of the organisms that fish like to eat. You may not, if you're in streams, and I know this is kind of a stream river network, amphipods or scuds, right? People don't often think about these things, but if you take, a sample of sediment in a stream or a river, you can see these things kind of crawling around. And so the importance of these organisms is, I'll show you here in a minute, but when we look at this graph on the right, what we see is a pretty noticeable decline in the abundance of these organisms when they're exposed to high salt concentrations. And so these things are consumed by things like yellow perch. And that's an economically important species where we come from. I mean, it's a multi-millions, tens of millions, or hundreds of millions of dollar industry here in the Great Lakes region. Now, I mentioned how important these are to yellow perch. In a lake that I worked on in the Adirondack Park in New York, what we find is that these amphipods are critically important in the diet of yellow perch. So when I say we're losing some of those food items like zooplankton and amphipods, that higher trophic levels, that is, smaller fish, larger fish, so on and so forth, this is a concern, is how will it affect some of our fisheries, that we value either for food or recreation. So when we kind of think about the long term here, and we think about a highly salinized system, these amphipods, or fish food, if you will, under a no salt environment, if you can kind of see my cursor, fish will eat these amphipods and then they'll produce a bunch of other fish. But the question remains, and this is something we're trying to address in some of our modeling studies, is when we reduce the availability of quality food resources, that the things that these fish need to survive, grow, reproduce, what's going to happen over the long term in these high salt environments. And so that's something we're working on right now through food web modeling studies. When we think about, I hope maybe if you can see this heading anyway, there's a lot of habitat that's important to organisms like fish and invertebrates in freshwater ecosystems. And one thing we've noticed in some of our experimental work is that we can lose some of the important macroalgae species. Some people think that this macroalgae in streams, slack water habitats in streams, wetlands, and lakes is kind of a nuisance, but some of these species are pretty important, and there's a lot of important species of macrophytes. And so as we increase the concentration of road salt in some of our experimental work, we can see that we get a pretty noticeable decline in that macroalgae species. Now, this macroalgae is important for a lot of invertebrates and small fishes to hide from other predators and to complete their life history and maintain a high population size. So what I've kind of just shown you is that some species are exhibit pretty severe declines in freshwater ecosystems. And then it's kind of a double whammy with the loss of some of this habitat, right? So something that needs further study, but some of these impacts are pretty alarming. When we think about organisms in stream ecosystems, we can think about rainbow trout. We did an experiment a few years ago on rainbow trout. And when we exposed them to no road salt concentrations and high road salt concentrations, we took them from what's called the alvin stage, right? When they hatch from an egg, they kind of have that yolk sac you see in the middle, and they're called alvins. And so when we expose them to high road salt concentrations for about 25 days, you can see on the right that the development is noticeably reduced, that these fish are much smaller than their counterparts in a no road salt environment. So again, we need to think about what could happen at higher trophic levels and how might this affect our fisheries long term. So when we think about protecting freshwater organisms and a lot of us, we're trying to identify the concentration at which organisms are going to exhibit some kind of negative impact. And so, federal governments provide some guidelines. And in Canada, they suggest that a chronic threshold, that is, the concentration at which a salt, chloride-based salt might exhibit, elicit a negative effect on an organism, is 120 milligrams of chloride per liter. And in the United States, that threshold is a little bit higher at 230 milligrams of chloride per liter. So do these work, I guess, is the question, right? And so some of us set out to answer that question with a broad scale experiment across the United States, Canada, and Europe. And so what you see here are the study sites where we exposed what are called limnetic food webs. So in the lake, the zooplankton algae food web to elevated road salt concentrations. And so we did this, you can see several sites, mostly kind of in the Great Lakes region, but we also have a few in Spain and 3 in Sweden and 1 in California. And so when we look at how the organisms respond among these different sites, what we have here is the percent change in abundance on this y-axis, and this x-axis, we have all those study sites that I just showed you. And then each one of these dots on this graph represents the Canadian threshold of 120 milligrams per liter, chloride per liter, and the US threshold of 230 milligrams of chloride per liter. So I've kind of taken the liberty to say that this dashed line, we see an increase in these organisms, and below this dashed line, we see a decrease in these organisms. And then we have this 50% decline line. And I think it's pretty clear that at the vast majority of these study sites, these organisms, cladospora and zooplankton are called, a critically important diet item for some fish species throughout their entire life, but almost all fish species during early life stages. And so we see this noticeable decline, suggesting that in a lot of lakes in North America and Europe, you know, these food webs may not be protected by these guidelines. So, and among all those study sites, at 47% of those study sites, we saw more algae due to the loss of those, we call them large body grazers, the Daphnia, in our experimental setups. And so again, we have that kind of clear water phase where we have a lot of zooplankton on the left, and then moving to the right, we have a lot more algae in the water column because we've lost that grazing pressure. So when we think about kind of a high level message, you know, of some of this work, we need to think about, well, what does this mean for like food webs? And so I showed you this graph on the left that when we start at the zooplankton, how will these, what we call planktivorous fish be affected, then the piscivorous fish be affected, and then all the benthic organisms. And so when salt pollution enters a lake ecosystem, in the example I just showed you, it reduces these zooplankton, which could have an effect on the fish. This increase in algal biomass from reduced herbivory, you know, has the potential to reduce benthic production. Remember I mentioned the scuds or the amphipods previously in this presentation? Well, you know, that's an important diet item for a lot of fish species. And so invertebrates like that could see, you know, pretty dramatic declines based on some of the evidence we're discovering. So, and most of this has been, you know, this is sodium chloride rock salt, right? The most common de-icer out there. So I think now what we need to think about is all the impacts you just saw were mostly from, like I said, it's like your table salt, same chemical composition as your table salt. And so the question becomes, there are several kinds of de-icing salts out there, and how are those affecting, you know, organisms in freshwater environments? And I think I'll turn it over to Bailey to talk about that now.
Thank you. And I will share my screen.
You're on there.
Okay. Can you see my slides?
Yes.
Yep,
Awesome.
good.
Okay. Thank you very much. And like Dr. Hintz said, I'm going to talk to you a little bit about some of the road salt alternatives that are available. He's just told you a lot about sodium chloride impacts. What are some of the impacts we've seen in some of the scientific literature, as well as some of his own work. And really, like he said, sodium chloride is the most commonly used road salt or road de-icer around the globe. And it's used because of a few reasons. One, it's really effective. Like he said at the beginning of his presentation, it reduces accident rate 87 to or 78 to 87%. And when you are going from place to place or getting your groceries or continuing our economic services that are provided on our roadways, that's really important to maintain. But also, it's really cheap in comparison to some of our other options that are available on the market, and it costs about $42 per ton. To put that in perspective, the graphic he showed you that he put into pounds of how much salt is applied to a roadway, we're talking about 35 billion tons, if I remember his graphic correctly. So he was at about 66, I think, for pounds. And so we're somewhere right in there, 30, 35. And so when we talk about how much salt is applied and we talk about $42 per that ton, that gets pretty expensive pretty quickly, but it is on the cheaper side of a lot of the other existing things that are available. Is a higher price for an existing alternative that exists, which we're going to talk about 4 main types of those today. Is that worth it if it's more environmentally friendly? And so that's really what I want to get across to you today is, are the existing alternatives viable solutions for reducing some of those ecological impacts that Dr. Hintz has talked to you about? And we're going to talk through 4 types of alternatives today, one being chloride-based, like our sodium chloride, one being an organic additives section, and we'll talk a little bit more about what that is, as well as some acetates, and then an abrasive. Most specifically, today I'm going to talk to you a little bit about sand usage in the winter as an abrasive, as an alternative for de-icing salt. First, we're going to get into those chloride-based. Well, like I said a second ago, some of these chloride-based alternatives are a little bit more expensive. For example, calcium chloride and magnesium chloride are not only the 2 most commonly used alternatives, but they are the top 3 with that sodium chloride of de-icers that are used around the globe, and as well as here in the United States. And they're growing in popularity, partially because they work really well in colder temperatures. They're a little more effective. And their expense in comparison to the sodium chloride at $42 a ton, calcium chloride is about $140 a ton, and magnesium chloride is about $111 a ton. And so they are a little bit more expensive, but some of them are being advertised as environmentally friendly. And we will get into some of the more specifics of what the literature tells us and what the science shows us in terms of if there are in fact more environmentally friendly than sodium chloride. But part of this is because of their effectiveness, you should be able to apply less salt to the roadways over time. And so whether or not that actually happens really depends on a lot of factors, but they should in fact over time be a little bit more, especially at those colder temperatures. And so when we get into some of the scientific things that we know about road salts, we can talk specifically about these chloride-based alternatives. This figure in front of you is a graphical abstract that we've been working on for a project that I've been working on with a couple of undergrads in our lab over the last few months. And essentially what we have here is those critical zooplankton species that Dr. Hintz talked to you about. I don't know if you can see my cursor or not, but at the top where it says D. pulex, D. dubia, D. ambigua, and then it has those EPA thresholds of chronic exposure and acute exposure of 230 milligrams per liter chloride and 860 milligrams per liter chloride. When we look at whether or not these chloride-based alternatives are in fact protecting some of those zooplankton species that Dr. Hintz talked about being so critically important to our food web, we can see that not only does the sodium chloride not being as protective as we would hope it would be across multiple of our common species, but our magnesium chloride alternative and our calcium chloride alternative not only don't look as protective as the sodium chloride might be, but they also look a little bit worse for our common zooplankton species. And again, this is unpublished. We are working on this project as we speak, but I thought it was a very good representation of some of the things we're starting to see come off of some current research. But if we move on to some of the previously published research, we can also see that we're not the only ones that are finding that these chloride-based alternatives might not be as environmentally friendly as they are being advertised as. This one study, 17, in fact, tested some of that those benthic stream communities that Dr. Hintz mentioned at the end of his presentation with the amphipods or scuds. And so a lot of insects have an aquatic life stage, and this study took essentially dishes and they put them in a stream in Colorado, and they then eventually randomly assigned and dosed each of them with magnesium chloride, and then they quantified what insect species existed within those stream mesocosms or trays that they had used for their experimental study. And what they found was that 69% of the community that existed there was made up of two main groups, mayflies and stoneflies. And of that 69% of that community, what they saw after they applied the magnesium chloride to these treatments, they saw the mayflies and the stoneflies at different milligrams per liter chloride concentrations reduced by almost half. And now one of these says 508 and one of them says 257. Now both of those are environmentally relevant concentrations that we see on a regular basis on some other work that we're working on, which is, you know, a little concerning when you talk about these are being used as potential alternatives to the standard. Additionally, we have other types of alternatives that might exist. I feel like I get this question the most when I tell people what I'm studying. What about the beet salt, right? And so the beet salt is really an organic additive de-icer, which means that it contains agricultural byproducts. That can be beet juice, that can be cheese brine, it can be some other byproducts. Some of them come from brewing and things like that. And what they're supposed to do is help the salt stick to the roads. So for example, this Beat It ice melter that you see here on the screen is actually 88 to 99% sodium chloride still. So they've really added this agricultural byproduct to it to try and make it stick to the road. And it's being, it can be applied as a brine or a coating to this rock salt. And it's supposed to help it stick to the road so that you can, again, apply less of it over time. Additionally, some of the marketing strategies advertise that it's more environmentally friendly because it could add some kind of nutrient subsidy to the environment. And we're going to talk about if that's actually what the research shows us right now. So this is actually a study by Dr. Patricia Gillis in Canada. And she did two studies that I'm going to talk about, and both of them focus on freshwater mussel species. So freshwater mussels are extremely important. They help with water quality. They act as food resources. They, in some settings, can indicate when pollution occurs because of the health of the ecosystem and because of their filtration jobs. And so they have a life cycle that contains what are called glochidia. And glochidia are essentially adult mussel larvae. And these glochidia attach to fish gills, and then they mature a little bit and they become juvenile mussels, and then they eventually grow back into this adult mussels and repeat the cycle again. But these glochidia are a vital part of this life cycle that our freshwater mussels experience. And Dr. Gillis has studied how some of our road salts can, in fact, affect some of this larval stage. And in 2011, she tested sodium chloride, so our standard rock salt that we've been talking about, on an endangered species of freshwater mussels on their glochidia. And she saw that the sodium chloride reduced larva ability in these glochidia larvae for that specific species. Now, what she also did was investigate different types of water whenever we are talking about toxicity levels for some of our species. So our EPA thresholds, they use a certain type of test that uses a specific kind of water known as reconstituted in order to determine those thresholds that we've been talking about tonight. And so Dr. Gillis tested that reconstituted water against what she refers to as natural water in her study. And she found that the water hardness of the water that you are testing the mussels in or the species in matters, and that potentially some of that reconstituted water doesn't have some of the things that your natural water would have in it. And so she found that reduction in glochidia larvae in that reconstituted water actually had a lower threshold for when that reduction would occur at such a dramatic level than when it would occur in our natural waters. And so she suggested that maybe some of the potassium chloride that is also being used as an alternative might be concerning, because potassium is a known toxin at elevated concentrations, at lower elevated concentrations, for our freshwater mussel species. And so whenever she did a different study in 2021, just last year, she tested our NaCl again as a brine form this time against a beet juice brine from that organic additive we've been talking about, and then the beet itself. And what she found, yes, the sodium chloride brine was damaging and reduced the viability of these glochidia larvae, but also that the beet juice brine had a 13-fold higher threat to these glochidia larvae, and the beet juice itself had a 19-fold higher threat to these glochidia larvae. And that is not only concerning, but she tries to go on and explain why that might have happened. And that brings me back to why I mentioned the first study. So what she talks about is how in this second study, they had the ability to kind of those nutrient levels. And they suggest in their discussion that the microbial communities might have experienced some nutrient influx, and that had encouraged them to spark activity, and that the potassium levels in the beet juice part of what is the beet juice alternative might have in fact been what is exceeding that toxicity level of the sodium chloride, because they saw that the chloride part of the sodium chloride was actually really low when those mussel glochidia started to struggle whenever they were talking about the beet juice. And because of the way they designed the study, they were able to make those comparisons and say, well, actually, this additive is adding potassium levels that are really, really dangerous. And so continuing to use this is concerning. And so further investigation before these become a standard needs to occur. And so really overall, these beet juice alternatives, organic additives alternatives might also be just as bad, if not worse, for some of our extremely important organisms. And with the current state of our knowledge, it's just not viable to use that as a new standard, right? And so if we move on to another option of the existing alternative, we have what are called acetates. We have calcium magnesium acetate and a potassium acetate that are two of the more common types of acetates. And you can see on this bottle that it's labeled as a natural alternative, but really it's dolomite lime and an acetic acid that are man-made together. So the idea of this being a natural alternative is something that we should further investigate, right? Again, we're talking about this being a lot more expensive now than sodium chloride, and potentially we don't really know how horrible or beneficial the impacts of this alternative might be, except for a few limited studies. And when we talk about, again, that trade-off, we want to know if the higher cost, which calcium magnesium acetate, for example, costs almost $1,500 a ton compared to your sodium chloride, $42 a ton, and potassium acetate comes in at about $1,100 a ton. When we talk about those increased costs for a potentially much lower freezing point, so it's more effective at those lower temperatures, and potentially natural alternative, is that natural alternative that they're advertising to us really better for the environment? And the truth is, we don't have a lot of information about these acetates just yet, but what we do have is also concerning for it becoming a standard. So this study from 2011 6 different chemical deicers, and also very important to ecosystems, and frogs in particular can be one of the first kind of indicators how those populations change when pollutants occur in an area because of how their bodies operate. And so this study looked specifically at 6 chemical deicers and how they affected the larval wood frogs. And of these 6 deicers, 3 of them were sodium chloride, calcium chloride, and magnesium chloride. So the 3 most commonly used road salts and the most commonly used road salt around the globe. Urea, which is a commonly used plain deicer actually, and then potassium acetate and calcium magnesium acetate. And what they found was that this potassium acetate and this calcium magnesium acetate were actually the highest, had the highest toxicity level to these wood frogs. So again, what we do know about them is not the best in terms of, are they more friendly? Well, the answer is no, and they might be worse. And so when we move on to an existing, other existing alternatives, we talked about chemical alternatives, we talked about those chloride-based alternatives and organic additive alternatives, and those acetates, but what about sand, right? What about abrasives that aren't necessarily made up of all of those things? Well, when we talk about sand, we have to talk about the fact that it is an abrasive. Its job is not to de-ice the roads, right? Its job is to provide traction between your tires or your feet. And that job and its effectiveness is dependent on what type of abrasive, so sand, and what that kind of sand is made up of. Is it silty or not? And if what temperature you're applying it at. All of those things matter, and they matter partially because of how effective they might be at providing you with that traction, but also partially because using sand as an alternative can contribute to things like winter air pollution. For example, if you can see my second bullet point here, you can see that the Colorado Department of Transportation in 1995 said that they could relate 45% of the winter air pollution in Denver to sand application that they were using at that time. And that's really concerning when you talk about being able to breathe in those harsh winter airs, especially if you're like me and you're from a little warmer of a region and you're like, well, you have an underlying health condition. Those are concerning statistics. And so when we talk about the potential of if these abrasives could be more effective, we have to consider all of the things that we have listed here. And we have evidence in the scientific literature that not only are they potentially contributing to other types of pollution, but they are also not as cost effective. The first study from 1996 created some ratios there where I've gotten my other numbers from, or at least the first author is, he produced a different study in 1992 that gave us some of those cost effectiveness. And the study in 1996 told us that they have a 0.8 to 1 ratio of cost to effectiveness whenever they're talking about sand as abrasives, meaning that you're losing money on that investment. And then this 1998 study is actually a study by a German scientist. And they essentially concluded that the effort that you have to put in to continuously reapply the sand for it to be effective, because like that fourth bullet point says, the friction capacity, even after light traffic, by almost 50%. And so continuing to reapply it is not an effective way of using your resources, and it's costing you a lot to do that. And so other studies have tried to make sand a better option for us by heating sand. Some people have tried to heat sand. The first people that tried to do it were in Finland. And they essentially didn't get it hot enough because the second study tried to do it and they heated it up even more than they did by, I think, about twice the heating capacity. And it was slightly effective, but not as effective as our sodium chloride is. And pre-wetting it or adding salt to it, also not as effective and not a viable solution for how to keep our roadways safe in the wintertime. And with that, I will take any questions, but I just want to say before I do that, because I missed the whole point, is that some of our key takeaways from not only my talk, but from Dr. Hintz's part of this presentation is that salt pollution can change the ecology and functioning of how our freshwater ecosystem work, and our current thresholds that are set in place are not protecting our freshwater ecosystems, and that these alternatives that exist might not be a viable solution for an ecologically for a more ecologically friendly alternative to our sodium chloride, especially when we talk about that on a large scale. Okay, so thank you. And at this point, I will take any questions.
Thank you very much. All right, so if anyone has questions, you can feel free to either put it in the chat and I will ask it aloud, or you can ask it yourself if you'd like.
No questions. All right. No.
Just had very good explanations. I guess there's not a whole lot of questions. I'm sure somebody has something. Well, I'll start us out then with one that about the use of beet juice as an alternative. So generally, when I'm asked about the use of beet juice as an alternative to road salt, my understanding is that it kind of being more of a sugar-based chemical, that it encourages bacterial growth, which can decrease the dissolved oxygen. Is that something that you've read as well, or am I pulling that from somewhere in distant memory that's not published?
Yeah.
There's a
Go ahead, Bailey. Go ahead.
There is, so yeah, that what it essentially does is it adds nutrients to this system, and that microbial community then produces activity, and when that microbial community is active, it then can reduce some of that dissolved oxygen that is existing within the water systems.
Yeah, I think, yeah, beet juice, I mean, it's kind of like a nutrient subsidy, right, in freshwater ecosystems. And so that, you know, just like fertilizers, it can be used by different organisms, and as you increase the respiration of certain organisms in the freshwater environment, due to that additive, that organic additive, you can see declines in dissolved oxygen. And so I think, you know, the high level message is we need to be careful what we come up with. Maybe, you know, science is always slow to catch up, right? And so I think we really need to kind of have some sound science before, you know, we really implement alternatives on a massive scale. So.
Okay.
Yeah.
if you're
All right,
looking
so we're
for a
getting
paper for
some-
that, there's
I
a
have a
couple.
question. Anybody hear me?
All right, so we're getting some in the chat box. We've got a question from Brenda. In my experience, the South is more likely to use sand instead of salt. How much does the sand cost, or is it easier to store and apply?
I'm sorry, I was trying to open my chat. So the sand, Bill and I were actually talking about this earlier today. So there's actually a shortage of sand. So applying it on a large scale comes with its own logistical issues. I am from the South as well, and I have not seen us use sand or salt, so I'm not really sure about that part of the regional aspect. My apologies.
Sand is almost exclusively used, I think, in Montana. There are some states also that, maybe not exclusively in Montana, but much more frequently in states where population density is really low. And so sand is generally cheap too. But there have been indications of sand shortages, Bailey just mentioned. So, and applying it on a massive scale, you know, as Bailey spoke about earlier, there can be nutrients in the sand, right? And then I think one of the other questions, since we're on the sand topic, you know, it can become aerosolized and when used a lot and reapplied. And so that aerosolization of the sand, you know, it can happen with salt too. You know, it gets in the air, and people that maybe have sensitive, you know, respiratory conditions can experience, you know, adverse effects, and it can bother your eyes and things like that. Some salinization in arid regions of the world, you know, when that salt dries up, it becomes aerosolized and can cause pretty significant respiratory distress and eye irritation. And so, so yeah, it sounds like a good alternative, but I think, you know, it requires some investigation.
Okay, I think Chuck, did you have a question that you were trying to ask? You're kind of quiet, but yeah, I can hear you.
Okay, well, I'll speak up.
Okay.
I'm calling from central Illinois near the University of Illinois campus. Around here, the State Highway Department uses liquefied salt rather than a granular, and I'm just wondering if that is worse than the granular salt, or and I know one of the reasons they do it is because so many motorists. I do the Adopt the Highway, so I talk to the people with the highway department, and if someone has a cracked windshield, they will claim that the rock salt did it. So they've gotten away from that and use a liquefied salt. One of the reasons for it. So you have these dishonest people taking advantage of the highway department. But I'm just wondering if that liquefied salt, and they don't do it all over the roadside, but always on the bridges, and before a snowstorm arrives, when it's predicted, they put the liquefied salt down.
Yeah, Chuck, that's a great question. And I'm going to share something. If you're phoning in, you might not be able to see it, but that pre-application of what's the salt brine is a good best management strategy. And so pre-wetting of materials or applying brines to roads before a storm really kind of prevents that ice from binding to the road surface, right? And that actually substantially reduces the amount of salt needed during or after a storm event. And so what you're seeing there in central Illinois is a very good best management practice, which I'm kind of showing on the screen here when we think about, brining or pre-wetting and applying salt to the road before a storm. So, I think that can actually reduce the amount of rock salt, for example, needed by I think some estimates are 70% during a winter storm event. So, we've spoken about the ecological impacts here, but what I just showed was a series of best management practices that, when leveraged appropriately and when salt's used appropriately, we can use a lot less and we can use it a lot smarter where it's needed, when it's needed, and things like that. So what you're seeing in Illinois is probably that kind of brining before the storm, which really makes removal of ice and snow much easier during the storm event. So the snow plows can do their job rather than having to just lay out a ton of salt and get rid of the ice and snow.
That's good to know. I'm pleased that we're being environmentally conscious of that. I have another question, if I may. With the concentrations of salt in the waterways, when the spring, how long is that retained? When spring's rains come, is it flushed, all the way through the watershed down to the main rivers, or what's the science tell us there?
No, sir. I wish I had a better answer for you, but salt can stick around for quite a while, right? And so, just because we go through one winter time, and Bailey can tell you this, we observed pretty high concentrations in Northwest Ohio just this past summer. And that's from decades of salt application and a few other sources, right? But when we think about a stream ecosystem, for example, there's this whole environment under the stream called the hypereic zone. And so salt can be stored in soils and groundwaters, and then recharged when it rains. That can be kind of, exuded from the groundwaters and increase surface water concentrations. And so salt, it's going to be the turnover time of the ecosystem of the water body, right? You can kind of, dilution is the solution to pollution, so to speak. But for salt, that can take a while. And so even if we turn off the salt source right now, salt will stick around for quite a while. And in some ecosystems, it'll stick around for, potentially decades. And so, that's kind of the concern, is that salt isn't biologically transformed. Chloride, that is, specifically, isn't biologically transformed. It's kind of called a conservative tracer. So, once it's in there for a while. And we really need to kind of think about that when we generate approaches to solving this problem, right?
Thank you.
Yeah.
Okay, we've got a few more questions in the chat from Gregory. What about other sources of salt, such as increased urban populations and wastewater, and the increased use of water softeners?
So water
Yeah.
softeners in residential areas, I mean, I can even go to a gas station here and pick up water softeners. Those are also inputting salt into our waterways, like Bill just talked about some of that groundwater. All of those things can be used as a potential source, including our wastewater treatment plants and agricultural things that he mentioned in the beginning of his talk. Even down to some of our manufacturing processes. For instance, some of our resins and acrylics and things, those have chloride in them. And those can also be other sources of some of the chloride or salt that we see in the environment.
Okay. Hannah asks, can sand affect stream quality by changing the sediment makeup or adding silt or something else?
Yeah, I think that's one of the problems is where's all that sand going to go? I mean, when we think it's got to go into sewer infrastructure first, right? And then that is going to have an outfall somewhere, or I mean, you got a whole wastewater treatment system. You've got stormwater systems, and so that sand could eventually trigger deposition in streams, and so there's a lot of gravel beds in streams that are important to organisms in the stream, and so it's quite possible that could change the habitat, the benthic habitat composition in streams. And I think that's one concern. I mean, has it been documented? No. I mean, there's a lot we need to kind of figure out about, how much stress on the systems that sand might trigger. You can see the piles build up where they use sand, and that has to go somewhere. So.
Okay. And Brenda, followed up to say that Texas seems to also use sand, but then also has a question. Could you repeat what you said about the difference in the reconstituted lake water versus natural lake water?
Sure, my apologies for the confusion. So a lot of the toxicity tests operate using what are called LC50s, and so they document, or they attempt to document when 50% of a population of what they're testing is reduced. And some of the, in order to keep that as standardized as possible, they make what is called reconstituted water. So it's water that is produced in the same way every time, and it can be reproduced by other types of labs and things. So it's water that is mixed together, and then actual lake water that you pulled from a lake. If that makes sense. I hope that was helpful.
Yeah, sometimes we want to use natural lake water in our experiments, which I think some of the ones we showed at the beginning of the presentation, it's just straight out of the lake, right?
Mm-hmm.
And then this reconstituted water, is kind of a way to generate ideal conditions to look at the effects of the salt. So everything out of the natural water, bacteria, viruses, things like that, to really identify the sole impact of the salt or the additive, right? So there are different ways of developing the science that may have different conclusions and applications.
Okay. Does the level of salt in our normally freshwater streams get to the point where it affects the osmotic balance in fish? Is that part of the lower growth of the fish in heavily salted water, or is the major detriment to the fish that of killing off their food sources?
Yeah, I think the study I showed you where rainbow trout growth was reduced, their organ systems haven't developed at that time. So when these organisms hatch in the stream, salmonids anyway, and they're those little alevins, they're feeding off that yolk sac that I showed you, right? And so they don't have the physiological, the anatomical machinery just yet developed in their gills and their kidneys, things like something called glomerular filtration rate, right? That's not developed yet. So they're kind of at the mercy of the salts and osmotic balance and stress. And so that might be one reason for the reduction in growth. And so there are direct effects on fish, like I showed you in the presentation. There's a study out of West Virginia that shows that really low salt concentrations in streams, I think it's around 115, 120 milligrams per liter, that salt plume causes fish to move out of the area. So it's not an impact on growth. It's not an impact, it's not going to kill the fish, but it can cause them to move to other areas, right? So that's kind of the behavioral effect there. And so, as I showed before, certainly there are several diet items that fish need to survive, grow, and reproduce that are directly affected by de-icing salts.
Okay. And I like to give credit for the question. So that one was from Deborah, and we have a question from John now. After the winter, when salt is no longer being spread, do zooplankton populations recover as chloride levels decline in warm weather, or do the declines carry over?
This is a loaded question. It's actually really cool, and there's some pretty cool science out there. So maybe I'll start with the long story, and Bailey, if you have anything to add to it, feel free. So we have some long-term studies from lake ecosystems that show the salt can accumulate in the lake, and it causes this turnover to salt-tolerant species, and that persists. You lose a lot of species, lose diversity of zooplankton. There's other zooplankton, but they may not be what we call functionally redundant, and it's not the same species. So you can get a different population, so to speak, or a different group of organisms. And so we have shown that zooplankton can evolve to higher salinity. Now, we don't know if that occurs in a lot of zooplankton or just a few select species. And so that evolution of a tolerance to higher salt, we thought that might buffer some ecosystems because organisms can adapt, right? One study we did kind of suggests not really, right? It doesn't prevent the loss and that cascading effect. So so long story short, the jury's still out. And I think what we need are like whole ecosystem experiments, right? We need to do some of those experiments in natural environments, and it's really hard to just find a lake and dump a bunch of salt in it. But there are groups of scientists that do this. And so I think some of those studies are forthcoming. And so we'll know more. But it doesn't appear that once a system is salinized, that there's going to be a recovery. And I think one message we need to be clear on is that salt just doesn't go away in the summertime. We might see peaks in the spring, during the spring snowmelt in lakes, wetlands, and streams, but that salt persists throughout the warmer months during the year. And so it doesn't just go away.
Okay, and I think we have probably our last question here from Gregory. Does increased chloride generally increase phosphorus release from sediments?
So yes. So when we think about phosphorus release from sediments, what do we need? We need a deoxygenated environment, right? Oxygen causes phosphorus to bind to iron, and it kind of precipitates out in the bottom. So locked up phosphorus in the sediments, what we need is an anoxic kind of environment. And so salt can kind of form a benthic layer, saline layer on the bottom of lakes. And there is some, preliminary scientific evidence. There's scientific evidence out there to suggest that that can trigger release of phosphorus from those sediments when you get that really briny layer that sits right on the bottom of a lake, for instance, or over sediments that have a lot of, phosphorus in them, so to speak. So yes, there is some scientific evidence to suggest that that phosphorus can be released, and then it can be used by things in the water column, by like phytoplankton, for example. So personally, I think a lot more work needs to be done on some of the, biogeochemistry, nutrient cycling in freshwater ecosystems. But, for streams, there's, a lot of the evidence suggests that they'll export more phosphorus and carbon and nitrogen and things like that. They'll export more nutrients downstream rather than kind of contain it, right? There's this concept of nutrient spiraling in streams, and streams are really good at transforming and taking up different nutrients into biomass of different organisms, for example. And so some of that function is reduced, and that those nutrients can travel further downstream. So yeah, a lot of work to be done. I mean, that's for sure, but I think the evidence is becoming clear. So.
Okay, great. Well, thank you, Bill and Bailey, for that great presentation, and thank all of you for joining us tonight. Before we let me share this real quick. Okay, so before you go, I wanted to mention that if you're interested in learning more about the impact of road salt on streams in your neighborhood, we have 2 upcoming volunteer training sessions for our RiverWatch winter chloride monitoring program. These 1-hour training sessions are online, and they'll be held on October 26th and November 14th. You can register for these from the event calendar on the RiverWatch website or the event links on our Facebook page. And then also our next Fall Speaker Series event will be held next week, Tuesday, and will feature a longtime RiverWatch volunteer and water quality advocate, Jim Bland. He'll be joining us to talk about some recent work trying to manage zebra mussels up in Lake County. We hope we can see you there, and you might see more things in the chat. I'm guessing that those are mostly people saying thank you. So, all right. And so good night. And I hope to see some of you again soon.
Thank you. Appreciate it. Very
Thank you
informative.
very much.
Thank you.
Thank you all. We
Yeah,
appreciate
for having us.
being with you.